In 1970, Soviet engineers fused a commuter rail car with twin-jet engines, chasing speeds that most thought were impossible for the era. Dubbed the SVL, this experimental rocket streamliner blasted toward 250 kilometers per hour, outpacing anything the USSR had seen. Yet it was doomed before it ever left the test tracks. If this was the cutting edge, why did it vanish without a trace? The real story reveals more than just forgotten technology. On July 23, 1966, a silver rail car streaked across the flat tracks of Ohio. The New York Central Railroad's M497, nicknamed the Black Beetle, was no ordinary train. Twin-jet engines salvaged from a B-36 bomber thundered atop its roof, pushing the car to a record speed of 296 kilometers per hour. That single test run set an American rail speed record and made headlines on both sides of the Iron Curtain. For the United States, it was a bold demonstration, a jet-powered train roaring faster than any passenger service in the country. For the Soviet Union, it was a wake-up call. In the late 1960s, Cold War rivalry had already spilled into space, aviation, and Olympic stadiums. Now the race for speed extended to the rails. Soviet planners and engineers, watching the American experiment unfold, saw more than a technical stunt. The Black Beetle proved that the West could turn even the most conventional machinery into a symbol of progress. In a world where prestige and technological achievement were inseparable, the Soviet Union could not afford to be left behind. Within 4 years, the response took shape in Moscow's design bureaus and railway institutes. The Ministry of Railways authorized a project that would push the limits of Soviet engineering. This was not about building a new commuter train or improving schedules. It was about demonstrating that Soviet science could match, and perhaps surpass, anything the Americans could put on rails. The challenge was to take a standard commuter rail car and transform it into a high-speed laboratory, one that could rival jetliners for velocity. This was more than a technical exercise. The SVL project was born in an atmosphere of institutional rivalry, where ministries, design bureaus, and factories competed for resources, recognition, and a place in the Soviet pantheon of achievement. Every new record was a matter of national pride. Every experiment was a chance to show that the USSR remained a technological superpower. The Black Beetle's 1966 run had set the bar. By 1970, Soviet engineers were ready to answer. The SVL, short for Skorostnoy Vagon Laboratoria, or High-Speed Laboratory Railcar, was conceived as a direct statement of capability. The program did not aim for mass production or commercial service. Instead, it was a showcase, a single prototype designed to prove that Soviet rails could support speeds that rivaled the world's best. The project's timing was no coincidence. The American record was still fresh in the minds of planners, and the political climate demanded a response that was both visible and dramatic. In the halls of the Ministry of Railways, the message was clear. The USSR would not simply follow, it would compete, and if possible, leap ahead. The SVL's mission was to claim a place in the international speed race, to remind the world and the Soviet people that innovation was alive and well behind the Iron Curtain. The stage was set for a technological duel between entire systems, each determined to outpace the other by any means available. As the SVL project moved from paper to production, the Cold War's newest front line ran straight down the rails. Work began with a standard ER-22 electric rail car, a familiar sight on Soviet commuter lines. This was no blank canvas. The ER-22's steel body offered a proven platform, strong enough for daily service, but about to be pushed far beyond its intended limits. Engineers at the Tver Carriage Works stripped away the usual fittings and reinforced the structure to handle new stresses. The boxy front and rear were reshaped with pointed nose and tail cones, each designed to slice through air at speeds few Soviet trains had ever approached. The lines echoed the aerodynamic logic of early bullet trains, but the intent was even more radical. The real transformation happened overhead. Technicians from the Yakovlev Design Bureau delivered two Ivchenko AI-25 turbofan engines, the same type used on the Yak-40 regional jet. Each engine, rated for roughly 3,300 pounds of thrust, was mounted on a sturdy frame above the cab at the leading end. The engines sat exposed, perched like twin turbines waiting for takeoff. Their combined thrust would push the SVL with the same force that launched a small jetliner down a runway. But here the destination was a stretch of iron rails rather than open sky. Inside, the passenger compartment gave way to a labyrinth of tanks, controls, and monitoring equipment. 7.5 tons of kerosene filled the new fuel tanks, enough to power a regional jet, now stored within the shell of a single rail car. The added weight brought the total mass to about 54.4 tons. The car stretched 28 meters from nose to tail, longer than a city bus and heavier than most locomotives in regular Soviet service. The center of gravity shifted upward, the roof now carrying both engines and much of the fuel load. Every detail of the conversion demanded careful adjustment, reinforced bogies to bear the extra weight, upgraded brakes to counter the immense momentum, and revised controls to manage the unfamiliar demands of jet propulsion on rails. The SVL's streamlined shape and jet-powered heart set it apart from anything else in the Soviet rail system. Even the name, Skorostnoy Vagon Laboratoria, or high-speed laboratory rail car, made clear that this was not a prototype for mass transit, but a rolling experiment. The project drew together railway engineers, aircraft designers, and factory workers, each group bringing its own expertise and expectations. The result was a machine that looked as much like an aircraft fuselage as a train. It was built to answer a single question: how fast could a Soviet rail car go when freed from the limits of wheels alone? As the last rivets were hammered into place and the fuel tanks topped off, the SVL stood ready, a hybrid of steel, kerosene, and Cold War ambition, waiting for its first run down the test tracks. On a cold October morning in 1970, a handful of engineers and test crew gathered beside the rails outside Moscow, watching as the SVL twin-jet engine spun up to a piercing whine. The car's heavy steel body, now reshaped and brimming with aviation fuel, sat poised for a run that would push Soviet rail technology to its limits. The order was given, throttles advanced, and in less than 15 seconds, the SVL surged past 50 kilometers per hour, an acceleration more familiar to pilots than to railwaymen. The sensation inside the cab was unlike any electric or diesel train. The floor vibrated with the force of 30,000 newtons of thrust overhead, and the landscape outside blurred as the car rocketed toward its target speed. The test section between Galutvin and Ozary had been chosen for its straightness, but even so, every kilometer brought new tension. At 100, then 150, then 200 kilometers per hour, the SVL held steady, the air roaring past its streamlined nose and tail cones. The crew, eyes fixed on gauges and dials, monitored every vibration and temperature spike. As the speedometer edged past 240, then 245, the chief engineer called out the numbers. At last, the car reached 250 kilometers per hour, about 160 miles per hour, before the throttles eased back, and the run coasted to a controlled stop. The SVL had doubled the average speed of Soviet passenger trains, which typically ambled along at just 40 miles per hour. In that moment, the jet-powered car became the fastest train ever to run on Soviet rails. The data from the run confirmed what the designers had hoped. The combination of aircraft-grade engines and aerodynamic shaping could push a standard rail car to speeds once thought impossible for the network. Wind tunnel tests, conducted earlier with 15 different scale models, had paid off. The car sliced through the air with minimal resistance, and the reinforced bogies and brakes performed under the intense loads. The SVL acceleration impressed the observers as much as its peak velocity. From a standstill, it could reach 50 kilometers per hour in as little as 10 seconds, a feat that left even seasoned railway engineers shaking their heads. Yet even as the technical team celebrated, the theoretical ceiling remained out of reach. Calculations showed that the SVL engines, if pushed to their limits, could have carried the train to 360 kilometers per hour, 224 miles per hour, matching the speeds of the world's fastest experimental trains. But the risks at those velocities were too great. The track, never designed for such forces, might not hold. The engineers agreed that 250 kilometers per hour was the safe maximum for the existing infrastructure. The SVL would not be pushed further. Still, the achievement was undeniable. In a single run, Soviet engineers had demonstrated that their hybrid of rail and aviation could match the audacity of any Western experiment. The numbers: 250 kilometers per hour, 10 seconds to reach 50 kilometers per hour, 54 tons of steel and fuel, were more than statistics. They were proof that, for one brief moment, the Soviet Union's rails had hosted a machine as fast and as bold as anything in the Cold War speed race. The vision for the SVL extended far beyond the test track. Planners in Moscow imagined a new era of rail travel, with jet-powered trains racing across the continent. The concept was bold. A high-speed passenger service, sometimes called the Troika Express, would connect distant cities in record time. Schedules were drafted, route maps sketched, and proposals circulated through the Ministry of Railways. The SVL, they hoped, would be the first in a new generation of express trains, shrinking the vast distances of the Soviet Union. The reality of the rail network cast a long shadow over these ambitions. The existing main lines, engineered in an earlier era, were never designed for sustained speeds above 140 kilometers per hour, about 86 miles per hour. Even the straightest, best-maintained stretches of track could not safely support the forces unleashed by a 250 kilometers per hour jet train. The rails, ties, and ballast would face stresses far beyond their design limits. Curves, switches, and crossings scattered across the map created risks that no amount of speed could overcome. Any hope of regular SVL service meant more than just running faster trains. Entire new corridors would need to be built, long, straight, and isolated from the dense web of freight and commuter traffic. Stations would have to be redesigned, platforms extended, and safety systems upgraded. Even the locations of stations posed a challenge. The proposed Troika Express, with its jet engines and high speeds, could not stop at the heart of crowded cities without major changes. New boarding areas would need to be constructed well outside residential neighborhoods, adding distance and complexity to every journey. The Ministry of Railways, responsible for every kilometer of track and every passenger timetable, became the gatekeeper of what was possible. Their engineers ran the numbers, reviewed the infrastructure, and weighed the costs. The gulf between the SVL's performance in isolated tests and the demands of daily operation proved impossible to bridge. No matter how impressive the prototype, the network itself was the final judge. The SVL was a technical marvel, but it was built for a network that did not exist. Without new lines, upgraded stations, and reimagined safety protocols, the dream of a Soviet jet-powered express remained just that, a dream. So the SVL's legacy shifted. Its data and design lessons informed later high-speed projects, but the grand vision of a jet-driven Troika Express never reached the timetable. The experiment had proven what was technically possible, but the rails beneath it answered with their own limits. In the end, the future of Soviet high-speed rail would follow a different path. shaped not just by engines and ambition, but by the hard geometry of steel and stone. The promise of jet-powered speed on rails collided with three problems that no amount of engineering could overcome. First came the noise. The SVL's twin Yak 40 engines produced a roar that rivaled a jetliner at takeoff. When the train accelerated past rural stations or through small towns, windows rattled and conversation stopped. Even on open stretches, the noise levels were so severe that planners calculated stations would need to be built far outside residential areas. An impossible demand for a passenger network meant to serve cities. Fuel consumption proved just as unforgiving. Each test run burned through tons of kerosene at a rate that dwarfed any conventional locomotive. The SVL's 7-ton fuel load vanished in minutes at full throttle. For every kilometer gained in speed, the cost in fuel soared. Soviet railway officials, already facing tight budgets, saw no way to justify such extravagance for routine service. The economics simply did not add up, but the greatest concern was safety. The SVL carried its fuel high above the tracks, directly over the passenger compartment. At 250 kilometers per hour, a derailment would have turned the car into a fireball. Engineers remembered the fate of earlier high-speed experiments, and one mistake could mean disaster. Safety reviewers refused to authorize higher speeds, knowing that a single accident would risk lives and destroy the program's reputation. These three obstacles, deafening noise, a voracious fuel appetite, and the specter of catastrophic fire, stood in the way of any future for the SVL beyond the test track. By the mid-1970s, the SVL project reached its quiet conclusion. The experiment had run its course, leaving behind a mountain of data and a single battered prototype. Official records closed the file on the Speedy Wagon laboratory, citing costs, impracticality, and the unbridgeable gap between ambition and reality. The unique railcar, once the pride of Tver's workshops, was set aside. No museum display, no grand farewell, just a move to storage at Doroshika in the Tver region, where the elements began their slow work. Paint faded, metal corroded, and the streamlined body that once cut through the air at 250 kilometers per hour settled into rust and silence. Yet the SVL did not vanish entirely. Workers at the Tver railcar factory salvaged the front nose section, preserving its sharp aircraft-like profile. Mounted on a plinth outside the plant, it became a monument to an era when Soviet engineers dared to chase jet-age dreams on iron rails. Today, the rest of the prototype is gone, scrapped, dismantled, its story scattered across technical reports and fading photographs. Only the nose remains, a silent witness to the experiment's audacity and its limits. For railway historians and curators, the legacy of the SVL lies not in what it achieved, but in what it attempted. The preserved nose in Tver stands as both artifact and question mark, a reminder of the moment when Soviet designers tried to leap decades ahead, and of the realities that ultimately called them back. In the shadow of that monument, the story of the SVL endures, a brief surge of speed, a long decline, and the memory of a machine that was, for a time, too advanced for the world around it. Today, the SVL stands as a silent warning. Technology can outpace the world it is built for. As modern engineers race toward ever faster trains, infrastructure and safety still set the real limits. The dream of speed alone is not enough. It demands a system ready to handle it. Progress always asks, just because we can, should we? Share your thoughts below.